Kia ora and welcome to video 11 in the series Insightful Integration. The problem in this video is very similar to the one in the last, in that we've got a curve that has a couple of properties. One, we're passing through a point 1, 2. Again, it just enables us to find some integration constants. But we also have this property that the tangent at any point x has a y-intercept that is the same value. So that's a little bit harder than the last video, and the differential equation you get is going to require this hint. You're going to need the substitution of y equals u times x, where u is a function. So give that a crack. Hopefully the substitution isn't too confusing for you, but it has been a past scholarship question, this type of substitution, numerous times, and so it could come up again in the future. All the best.
Okay, so this problem here is very similar to problem 10, you might have noticed. It's got a curve that we're trying to find. It's got a couple of properties here. Problem 10 was circle, and the circle is quite easy to identify using simple geometric properties. However, this one here, a little bit harder to conceptualize, and it comes with a differential equation that needs a hint to solve it. And the hint is quite a common one. It's appeared in scholarship problems before, where you make this random u times x substitution, and you substitute that product in, and it makes the differential equation turn from a linear, what is defined as a linear differential equation, into something that's separable, and we'll look at that when we get there. So first up, we need to again conceptualize it. So we've got some picture where at some point x equals a, and the reason why that's used is to talk about a specific point on the curve, but let's just say at any point x. At any point x, the tangent at this point, so let's just draw some random curve, the tangent at this point goes through the y-axis at the value a. So if I choose x to be x, then that's also going to equal x. Obviously my diagram's not to scale, or my curve is not the appropriate curve, because that clearly looks bigger. The y-axis intercept there looks bigger than the x-intercept, or the x value I started with. But never mind. Alright, the tangent, the gradient of the tangent there is just given by dy dx. And that's equal to, just like we did in problem 10, just change the colours to make it easier to see, it's equal to this slope of this triangle here, which we can find using rise over run. So we've got x is the run, and bear in mind that that coordinate there, that coordinate is x comma y. We don't know what the equation is for that curve, so we don't know what y equals, but xy is the general point on the curve, and therefore the height of this triangle here is x minus y, assuming that the y-intercept x there is bigger than the y value we started with. Okay, so we can equate those. The gradient there, x minus y divided by x, and this is not a separable differential equation. We could try and separate it, but we're going to run into a few problems, because dy dx there is equal to 1 minus y over x, and it's a difference of two things. 1 minus y over x doesn't separate because it's not a product of things. So that's where this hint comes in. The hint suggests to replace y with u times x, and in the thing it says u of x to tell you that u is not a constant, it's a function. But I'm just going to let it equal u. Okay, so this here I'm going to say let y equal ux, and apparently that helps us. Okay, how does that help? Dy dx equals, whoopsies, don't get rid of the 1 minus ux over x. Doesn't look like it's helped much. It has cancelled those. I think on the outset of this video I talked about linear differential equations. What we're looking for actually is differential equations where y over x appears. when y over x appears, a substitution of u equals y over x is helpful. But the issue now with our differential equation is we've got three variables in it. We've got the u variable that we've introduced, and then x and y as we had to start. So we need to go back to the substitution like we do with any substitution and integration. We need to differentiate it. So if we go dy dx, this time we need the product rule because we're differentiating not a number times x but a function times x. So the derivative of y with respect to x, differentiate the first term times x, differentiate the second term with respect to x, which is 1 times u. That's the product rule there from differentiation, and that's equal to du dx times x plus u. That enables us to get rid of the y in our differential equation. Okay, so if I go back to my differential equation, oopsies, I'll just hide that graph. I've made the graph for what this actually looks like. So du dx x plus u equals 1 minus u, and then we can simplify that, do a little bit of rearrangement. Something's gone wrong here. What is the something that's gone wrong? Oh my goodness, right back at the start. Hopefully you picked up on this, but if I take, let's use a different color pen. If I take x minus y, which is a positive number, and I divide it by x, which is a positive number, I don't get a negative slope, but the tangent's clearly a negative slope there. So x minus y, this dude here needs to be switched around. So we get y minus x over x, and therefore we get y over x minus 1. Okay, that actually makes a big difference because it enables us to actually be able to solve this thing. I got down to a differential equation that still wasn't separable. There was a bit of an issue there. Okay, cancel. Now we've got du dx equals negative 1 over x. Much nicer. And we don't need to separate that, we can just anti-diff it. U is the integral of minus 1 over x dx, and that's negative ln x, but also remember that u is equal to y over x, because we need to go back to the original variables. Negative ln absolute value of x plus c. Were we told some initial conditions? Yep, passes through the point 1, 2. So when x is equal to 1, y is equal to 2, that gives us 2 equals negative ln 1, which is 0, so c is equal to 2. And y over x equals negative ln absolute value of x plus 2, which we can multiply the x up and get it in explicit form there. And that there is the equation of our curve. Apologies about the error in the middle there. So, okay, what I've done just to finish this video is I've made a little picture. That blue curve there is the function y equals 2x minus x ln absolute value of x. You can play around with this on Desmos or GeoGebra if you want to. And then I've looked at 3 different tangents here. So the first one here, this purple, not purple, red. I guess it is purple if I shade in the red with blue. X equals 4. See that the tangent goes through the y-axis at 4. And the black tangent there is the tangent drawn to the curve at x equals 1. And it has a y-intercept of 1. And then the green one is a tangent drawn to the curve at minus 2. And that goes through the y-axis at minus 2. So it's showing that the shape is correct. It's quite nice that it's a symmetrical curve. I think about why it might have some symmetry about the origin there. But there we go. Hopefully that picture helps you understand why it wasn't a simple circle like question 10 in the series was, and why we actually had to solve a differential equation to get the result. The differential equation itself was a little bit messy. First up, I had to derive it from a picture, and I had to make sure I got it right. Secondly, that substitution of letting u equal y over x, or y equals u times x. Like I said, it's quite common, but basically that enabled us to solve the differential equation that wasn't separable. If the differential equation is not separable, you will be given a hint in a scholarship problem to attack it.